yeah, now we have started the recording, and also I should say very warm greetings from Bastian Koller, who cannot be here today. And he asked me to give a little bit of an introduction to EXCELLERAT, what it was all about the last 3.5 years, what's the idea behind it, and yeah, wish you all a lot of fun with the online conference. As said, we have almost 3.5 years of project runtime behind us, during which we tried to establish EXCELLERAT as the Center of Excellence for Engineering Applications in Europe. So we try to make EXCELLERAT the central access point and central competence hub if one wants to do HPC and especially HPC towards exascale in engineering. I think we have initiated quite a bit of actions and quite a bit of stuff in this conference. We will give you a few technical details and a little bit of an overview what was done with our use cases, with the codes, what we achieved in our journey towards exascale for engineering. And of course, the idea of EXCELLERAT is to interact with the community, to establish a central access point for know-how transfer and competence in the field of engineering that is, of course, living from interactions and with the community. So please feel free to ask questions. Please feel free to interact and contact us. As said, the first funding phase of EXCELLERAT is now over, but of course we are pushing forward and trying to extend the complete project, and with hopefully second funding phase and the pre-exascale and exascale systems at the horizon, we will try to prove what we promised, to move engineering towards exascale and show meaningful results with it. And with that, again, I would like to introduce our first chairman, Mark Sawyer from EPCC, who will moderate and handle the Q&A section of the first session. And after the short break, Andreas Wirse from the CCOS BW will take over and be your chairman for the second part. And with that, handing over to you, Mark, and wish you all a lot of fun.
Thank you very much indeed for that introduction, Ralf. So as Ralf says, I'm going to be chairing the opening session of the conference. And so just as a reminder that if people have questions for any of the speakers, the best way to do that is through the chat window, and then I'll be taking a look at those as they come in, and we'll deal with those at the end of the presentation. So thanks for your attention to that detail. So I'm going to introduce the first speaker, who is Agne Cerniauskaite from the European Commission, and she's going to speak on the HPC strategic priorities of the EC. Agne, floor is yours.
Mark. Thank you. Let me share the screen with you. You should see now the slides.
Yes,
correct?
Perfectly fine.
Yeah.
Yes, we do.
Okay.
Thank you.
Hi, so as Mark said, I am Agne Cerniauskaite from the European Commission. I work at the HPC and Quantum Technologies unit, and I wanted to talk a bit about the HPC strategic priorities at the European Commission. Today I'll speak about the new developments in HPC, its state of play in the EU, notably the achievements and plans of the Euro HPC joint undertaking, and the outcome of the fitness check that EXCELLERAT also made part of in 2021. and which was assessing the centers of excellence for HPC applications. In 2021, the European Commission presented a vision for Europe's digital transformation by 2030. It proposes a digital compass for the EU's digital decade and that evolves around 4 cardinal points. So we have skills, infrastructures, businesses, and government. And in order to achieve these 4 cardinal points, quite a lot of political and financial effort was brought into. We have several framework programs and also initiatives like the Euro HPC joint undertaking that are working towards this goal. And this year in January, the Commission also proposed interinstitutional declaration where it wants to assess annually the progress, which shows really the determination and political will to get into this digital era. So we have the EU Recovery and Resilience Facility that 20% of those 670 billion will go to the digital transition in each country. We have European Green Deal that we will contribute while trying to make the carbon neutral or green machines, let's say, or pieces of the machines. And also we have the Euro HPC joint undertaking as an initiative. What led to the development of such EU strategy was the low level of investments in the domain, the exponential growth of the data and the need for high-end computing performance, the recent quantum race, and a lack of European technology in the field, like digital sovereignty issue, that we are more and more dependent on the non-EU based technologies and infrastructures. So what is the role of the Euro HPC in all this? Tomorrow you have a session and my colleague Claudia Scaleza should present you more about the Euro HPC joint undertaking. I'll just mention that, okay, it's an legal and funding entity that was created in 2018. And in 2021, it received a renewed mission to better align its goals to the EU digital strategy. And it, according to the new multi-annual financial framework, it will get 7 billion euro of the public and private total investments. And the new elements for this 21-27 period are the such like infrastructure like quantum or hybrid HPC quantum computers, the hyperconnectivity, the federation of resources. On software part, the European microprocessors like EPI or RISC-V, also the applications that should be optimized for the EXA and post-Exascale systems. And we also support the climate neutrality and digital leadership transition through the international cooperation. So for this slide shows what has already been achieved from the infrastructure point of view. So we have already procured through the GU 5 petascale and 3 pre-exascale machines. That acquisition is about 510 millions in total. And it follows the digital decade's vision and the mission of the GU in order to assure the secure and integrated world-class HPC infrastructure. Now, a second part of the infrastructure's updated mission is introduction of the quantum, industrial grade, and post exascale supercomputers. What you see in this table in green, this is what we have already achieved through the GU, and what you see in the columns 2025, 26, 27, this is what we are going just to do. This is our plan. Also, for this mission, we were counting on the federation of all these before mentioned resources and interconnection of them with the European public data, so that the majority of the businesses, starting SMEs and finishing academia and industry, public sectors, they could use the cloud services and high-speed connectivities. We have already ongoing projects like Destination Earth. That's one of the examples where we try to tackle the climate change through the HPC calculations, and also human digital twin, which is the, let's say, e-health sector, and in silico simulations of the human body. And this is most probably for today's audience is the most important, interesting point, that the GU has all these three pillar activities like infrastructure, technologies, and applications, where it makes effort to make them interconnected and going step by step, hand in hand. And this is where the centers of excellence come in, also the national HPC centers of competence, in order to develop and support the advanced applications optimized for these exascale systems. And of course, also to help to develop the key skills that European science and industry needs. And very quickly for the centers of excellence, the fitness check. So the main objective was to check 16 centers of excellence that were finished or ongoing at the time. So the oldest was started in 2015, and the last one was just started in 2021. We wanted to see if the centers of excellence is working as an instrument, and if we should change something or not about it. The main achievements of this fitness check was drafted by the 5 experts who evaluated all these 16 projects. They made the comments that, okay, the technical progress on the applications was excellent, which is great, and which shows that we are on the right path. Currently, it was just for Terra and petascale, so there is a place of improvement, of course, but we are already on the right path. That all the centers of excellence are well engaged with the relevant community. Some, but not all of them, have industrial and HPC and end user roles integrated in their governance. Their training programs are of high quality, and collaboration with praise was very strong. This is what they drew as a very positive points from this fitness check. Nevertheless, as often, there is a space for improvement. And what the expert noticed was that, okay, we are not at the exascale level yet, and only few applications are working at that level. That co-design with the HPC vendors is pretty much sporadic, and it complicates a long-term trusted relationship and continuous development. Also the training programs are of high quality, but the coordination of those training programs was quite weak, and the offerings were not fully coherent. Also, a bit limited engagement with industry, especially the SMEs. The sustainability and business planning were beyond the current project funding was pretty weak, so there was little about the long-term vision, and the definition of KPIs was quite limited, let's say, or not challenging enough. Also, the few source codes have been an open access, and the collaboration among the centers of excellence themselves has been pretty limited. Also, there have been some positive examples of this collaboration. And with also the collaboration with European HPC projects, other projects also was quite limited. The experts drew also the recommendations. So they expected that more dedicated focus should be on put on exascale capabilities, that the long-term strategic partnership with Europe and exascale stakeholders would enable centers of excellence to contribute to the design of future systems while providing them with a better vision of the infrastructure roadmap. So that's pretty important point, that the limited numbers of exascale COEs we had at the time. So we hope for more COEs that challenge the exascale levels, and we expect that the trainings to foster the evolution of European research communities. So as well as enhance the cooperation with among the EU projects. So that was about the fitness check. And the news that most probably all of you know, that the National Competence Centers for High Performance Computing, the call was published, and its deadline is the end of June. It has the aim to support existing national competence centers and to create the new ones. So we decided to leave it as an instrument in Europe. And it has, the applicants are invited to submit the proposals for 2 topics, one on the national competence centers themselves, and another on the networking and coordination of these competence and centers. I also put the link below that to the EuroHPC GU's website, where you can see more details on the calls. I hope it was useful, and thank you for your attention. I don't know if we can go on with the question and answers. Mark?
We have a few moments here if anybody has a question then that they'd like to put to Agne.
Okay.
If anyone has a question, they can post it into the chat. Okay, I don't see anything arising there. So I'd like to thank Agne for that presentation. I think there was some very positive stuff that came out, positive comments that came from the fitness check, and also some useful pointers for how to steer the work in future. So that's always very useful feedback to get. What we'll do now is I'll move on to our next speaker, who is Dennis Grieger from HLRS. And Dennis is going to talk about the journey of in-situ visualization with Vistle. So Dennis, when you're ready, the floor is yours.
Yes, hello. I hope you can hear me.
Yes, works well.
And you can hopefully see my screen now. Can you?
Yes.
Okay, very nice. So welcome to our journey of in-situ visualization with Vistle, driven by one of EXCELLERAT's simulation codes, NEC 5000. And I will jump right into a little motivation why we did this. So we do the simulations to generate some knowledge, and usually this is done by creating a lot of binary data that is then stored on disk after or during the simulation, and then is read into third-party software to do the analysis. And in the last couple of years, simulation have been increased through parallelization of the computing resources, so more CPUs instead of faster CPUs. But this principle couldn't be applied in the same order of magnitude to hard drives or the data I/O, and therefore this becomes more and more of a bottleneck for these simulations to write the data to disk. And that's why we want to postpone the post-processing a little bit to the step before the data is written to disk, and then we can write the compressed and already partly analyzed data to disk, which saves a lot of data. And this allows us then to focus more on the data we already interested about, by setting up this post-processing pipeline to the fields we want to know. So for example, if we want to know a special ISO value or are interested in a special region, we can adjust this way easier than doing this in the simulation code. And another benefit is that we can already have some insights into the simulation, and this allows us, for example, to detect errors quite early, which can save a lot of money if we speak about exascale simulations. And another aspect of in-situ visualization or post-processing can be the simulation steering, which allows to send data back from the post-processing software to the simulation to, for example, change some bounding conditions dynamically, which we actually haven't done yet, and which is a part of future works. And the code which we wanted to use for the simulations, in our case, is NEC 5000, a computational fluid dynamics solver, which is highly scalable due to the spectral element method it uses. And one part why we chose NEC is because it already had an in-situ interface for a common post-processing software called Vistle, and the corresponding interface is called LibSim. And we want to couple the simulation code with Vistle, the simulation software we are developing here at HLRS. And Vistle is a scalable visualization platform optimized for virtual reality, which means that you can analyze complex 3D geometries quite comprehensively in virtual reality. Vistle is also very modular, which means that it can be easily extended, in our case, for a module that connects to simulation and get us the data. And Vistle is distributed, which means that you can combine multiple Vistles on different clusters together, which in terms of in situ visualization has the effect that it would also cover in-transit visualization or post-processing, which means that you only gather the data at the computation cluster, and then you send it to a post-processing cluster, which then processes and writes the data to disk. But at the start of the project, Vistle didn't have any in situ capabilities, and that was the main job that we had to do to implement these in the EXCELLERAT project. And to do this, there are a couple of existing approaches. So as I mentioned, NEC already had the LibSim interface, which is a proprietary interface for the visit post-processing software. And the same applies to the ParaView, another common post-processing software, which has its own proprietary interface. And we could have done something similar for Vistle and NEC to implement an interface, especially for Vistle in NEC. But we didn't want to go this route because it's not really scalable. It would force other simulation developers to basically put in the same amount of work to make their visualization software capable to run in situ with Vistle. And so we chose to do a more general approach. And there the SENSEI interface comes in quite handy, which is exactly what we need here. It is an interface that couples both an simulation interface and a backend interface, which then allows simulations that are instrumented with SENSEI to couple with any of the backends that implement the SENSEI interface. And so we decided to implement the SENSEI interface for Vistle, and for NEC. But the first step for NEC was to also try to adapt an interface for Vistle that can connect to the LibSim interface, which even though it's proprietary, all these codes are open source, and therefore we started with what was given and connected to the LibSim interface. And what we had to do this is to build basically a fake LibSim library that then passes the data to Vistle instead of a visit. And also to make this work is to fake the TCP communication where this interface is based upon, and use this to connect to the simulation. And what this allows is that the simulation thinks it is speaking to visit, but it is actually to Vistle. So for simulation developers, it is no difference. It's just one change library. And then after we had the LibSim data in Vistle, we had to figure out the data format that Visit uses and to convert it to Vistle, which also implies for Vistle that we copy the data to shared memory, which is a little bit unfortunate, but also allows us in terms of memory usage, but it also allows us to be a lot more flexible with the data and keep it as long as we might need it for our interactive virtual reality visualization. And after data was converted, we then had to somehow inject it into the Vistle pipeline. And therefore, we created a Vistle module, which is a little bit special since it had to allow the communication with the simulation on the one hand and with the user on the other hand. And but yeah, after we had this figured out, We then had first results with NEC 5000. These are two of the example codes that are, or simulations that are shipped with NEC. On the left side is a 2D simulation, flow simulation around a cylinder. And you can see the pressure heat map here. And on the right-hand side is a 3D flow through two endless plates. And you can see in the background the pressure, isosurface, and the velocity is displayed as these green streamlines on the right bottom side of the image. So then the next interface we implemented for Vistle was SENSEI. And here it was quite a lot easier to do the actual implementation, because we the interface is made for backend developers to do this, and we could just implement this analysis adapter. But we struggle a little bit with exporting our libraries so that SENSEI can consume them to convert the data to Vistle's format. And therefore we had to adapt our build system that's based on CMake a little bit to export our libraries for SENSEI. And on the way, we also had to fix our VTK converter code that we already had, which also made it easier in some points, because SENSEI is VTK based, and which is a common visualization toolkit that a lot of these post-processing softwares use, but not Vistle. And we could also use quite a lot of the previously implemented LibSim module to create a module that basically does the same for SENSEI. And meanwhile, in NEC 5000, during the EXCELLERAT project, they developed adaptive mesh refinement, which means they can dynamically increase the resolution of the mesh in parts where, for example, there's a lot of dynamic in the data that's simulated. And unfortunately, the existing LibSim interface was not compatible with this change. And excuse me. Therefore, yeah, the EXCELLERAT use cases that we actually wanted to use to demonstrate and test the in-situ visualization with bigger cases, they all use this new adaptive mesh to increase their scaling. And therefore, we basically had no visualization of a production case with the existing interface. And they actually put in another interface, the Catalyst interface, which we hadn't implemented. So we still had a little bit of work to do here. And fortunately, the Catalyst interface helped a lot, since it's also VTK based, and we hadn't figure around with the Fortran 77 code of NEC 5000, which is quite unreadable, I want to say. And we could use this existing Catalyst interface to rebuild a SENSEI interface quite easily, where again, the linking was the major issue with SENSEI, since we had to link NEC to SENSEI, which then links to Vistle, and NEC uses its own scripts to create its make files or its linkage, since it usually depends all its dependencies in its own repository. So this is no problem for a normal NEC version, but for this it was quite hard to link it all together. And so we again rebuilt the build system for NEC with CMake, and forgot, unfortunately, some compiler flags, and got the unfortunate results you can see on the right-hand side, which we fixed. And hopefully we can show you how it looks like now in our cave. I prepared a actual run of the demonstrator case of a helicopter rotor simulation on Hawk with 8 nodes and 200 56 ranks, and we will now jump into the cave, and where have I have to switch the camera. I can't do So we already loaded in a 3D model of a helicopter. It actually doesn't have anything to do with the simulation. It is just to give a visual indicator on what's going on. And also, okay. So what I did is, unfortunately, I can't share the screen on. Thank you, Uwe. On the other screen, but now you could see that the simulation is executing in time step, and Vistle is processing the data. And now, right as it came in, the data is visualized as these isosurface around the blades. The actual blades of the simulation had a little bit different shape, so it doesn't look that accurate. And we can now process the next time step, and it takes some time since it's not as it just updated, and we can also just run the simulation while the simulation is running, and we can configure the interface so that we can see every now and then the new timestamps that the simulation is processing. Yep, that's basically it from our side, and thank you for your attention. I think the Q&A is after the next talk, right?
That's right, Dennis. So I'll thank you for your talk and your very nice demonstration of the virtual reality environment there. That was very brave to do that live. We'll move on then to the next speaker, and that is Saleh Rezaeiravesh from KTH, who's going to talk about UQit, which is a tool for uncertainty quantification in fluid engineering. So Saleh, when you're ready, the floor is yours.
Thank you very much. So I'm going to share my screen. Hopefully you see it now, right?
Yes, we see it. Thank you.
Okay, yeah, thank you. So thank you, Mark. I'm going to talk about UQit, which is a tool for uncertainty quantification in fluid engineering. So UQit has been mainly developed during the course of EXCELLERAT. This is a joint work with Philip, and we are from KTH, Royal Institute of Tech in Stockholm, Sweden. So in this presentation, I'm going to start from a short introduction to uncertainty quantification and say why we need that. And then we move on to UQit, and we talk about the main feature of that. Afterwards, we are going to look at some examples and applications. So let's consider the wall-bounded turbulent flows as an example of general fluid flows. So it's very easy to find examples of this type of flows. For instance, we can look at the flow over the body of cars, airplanes, and ships. So if we would like to know about these flows and gain knowledge about them, we have different approaches. So we can conduct laboratory experiments, or we do computer simulations of different fidelities. And these days, if you have a set of data from different sources, we can combine them, construct low-order models, surrogates, meta models, and do some analysis based on them. And usually it can happen that we combine the information that we get from these different approaches. But there is one problem. For all of these approaches, there are different sources of uncertainty which are going to affect the knowledge that we gain. It's very important to quantify those uncertainties because we are going to use our current knowledge in order to do some extrapolation and make predictions. First of all, we should know that error and uncertainty are not the same usually. So this is a graphical representation of these two concepts. So having a scattering in the data is usually being considered as some level of uncertainty. But in comparison, error is just being close to some target or reference value. But the good thing is that, as we will see, we can use UQ techniques in a way to measure even errors. So why do we need to have UQ? First of all, we would like to estimate the influence of various parameters on the simulation's outcome. So if we have some turbulence simulation or flow simulations, no matter how large they are, we should be sure about the robustness of the results of those simulations. And we should make sure that they are not going to change a lot with the different computational numerical parameters. So we should have some understanding about the influence of such parameters. Also, if we have given some CFD data, which have been gained by a simulation on different sources from different fidelities, we should be able to assess the uncertainty in the data. But aside from this, there are UQ-based algorithms for optimization, data fusion, prediction, and so on and so forth. The first problem is about estimating influence and sensitivity with respect to various parameters is usually referred to as the UQ forward problems. In contrast, we have UQ inverse problem when we have a set of observed data and we would like to infer some structural functions, some parameters based on these data, and those functional parameters are going to be uncertain. And usually in practice, we should combine different forward and inverse problems. But it's not so straightforward to apply UQ techniques in turbulence simulations. There are at least two challenges involved here. So first of all, if we consider this range of numerical approaches for flow simulation, for turbulence simulations, we see that we have low fidelity approaches like RANS, and if we move forward toward higher fidelity like LES and DNS, the computational cost is going to increase, especially at very high Reynolds number, which are usually relevant to engineering applications. The use of, for instance, DNS or very accurate LES can be off the table. On the other hand, no matter which of these fidelities is used for simulation, there are different sources of uncertainties involved. But usually at low fidelity models, the modeling uncertainties are dominant. But at scale resolving approaches like LES and DNS, these are the numerics which play the most important role. But in any case, these uncertainties are there. We have to have a good understanding about their effect on the results. UQ is one of the main technologies that has been considered in NASA Vision 2030. So if we look at this technology development roadmap, we are almost here, 2022, and we see for UQ, we should be like from low toward medium readiness level. And we would like to have reliable error estimation in CFDs or uncertainty propagation capabilities and larger scale stochastic capabilities, for instance, by 2030, as some standards for the next generation CFD codes. So it's good to start from now, and that's what we were thinking about. So we have started developing this UQit, which has been written in Python, and it's a package for UQ in CFD. Currently, there are modules for prediction and data fusion, mainly based on the Gaussian processes. There are modules for uncertainty propagation based on Monte Carlo, standard and probabilistic polynomial chaos expansions. We have global sensitivity analysis, for instance, by measuring Sobol sensitivity indices. And we have a major module for time series analysis for prediction, for signal extension, and also for estimating uncertainty in different turbulence statistics. So the code is open source, and one can have access to the code from here. And why we started doing UQit, or what do we have in mind when we started developing UQit. So we would like to have a module which is very efficient and easy to develop and expand. So we have chosen Python, and as we know, there are many open source Python libraries for statistics, machine learning, data science, which have very close connection to uncertainty quantification. Also, we picked up the object-oriented programming for UQit, so one can easily expand the codes and implement new approaches. So UQit is versatile, which means that it can be easily linked to any CFD solver provided having the interface. So we have been preparing a very pedagogical interface. It's like interactive documentation and many examples in Jupyter notebooks. We have academic support via ongoing PhD projects. Some part of those development in this project will be released as a part of UQit in the end. But the most important thing is that we would like to have a state-of-the-art technologies related to UQ, which are applicable to CFD applications. So we can consider this workflow. There are UQ-related questions driven by an academic or industrial application. Then we do the theoretical and algorithmic development. Then we implement those techniques in UQit, write tests, preparing documentation, and make some publication and dissemination. So in the end, when the publication is out, we can release the source code, unless the question is from some industrial sector, for instance, and there are some licensing issues. But the aim is that we keep the UQit open source as much as it is possible. So simple example about the non-intrusive interface with any CFD solver. So imagine that we have this ellipse and we have two parameters, L and D, which are controlling the size of this ellipse. And we would like to understand how the variation of these two parameters is going to affect the outcome of the simulations. So for various samples of L and D, we can run the simulations. So at the first step, we generate mesh, we run the simulations, and here we have the data extraction step. So it can be either in situ, for instance, related to what Dennis was talking about, or it can be just from the data which is stored on the disk. Later, we send this to UQit, and we can combine the data and make predictions for the mean process and also the associated uncertainty. Of course, this is a simple example, but let's move on to a more advanced examples, perhaps. So recently, we suggested a framework for combining parametric and observational uncertainties in computer experiments related to CFD. So we have numerical computational parameters which are controlling the accuracy of the simulations. So for a limited number of samples from these simulations, we can gather the time series data and we can estimate the uncertainties. Later, we can combine the uncertainty from these time series with the variational effect from the original parameters and answer three main questions. How much the error in different quantities would be varying over the space of Q, considering the observational uncertainty. Second is that how sensitive the data or the outcome are with respect to the variation of the parameters when we have some uncertain data. And finally, what is the contribution of each of those computational parameters in the accuracy of the final computed value? A main part of this workflow is about estimation of time averaging uncertainties. So as we said, UQit has an extensive module about time series analysis. So the idea here is that we run a simulation, but in any case, we have to stop it at some point. There will be some finite time averaging, which is going to lead to some uncertainties in the computed statistics. So it's important to measure, for instance, for the mean value of a signal, we measure the uncertainty as the time averaging is going on. So we can monitor the reduction of the error in the some sampling estimator or other statistical term. So regarding this problem, we have implemented various estimators, including autoregressive and autocorrelation-based methods, and also batch-based methods. Also, we have proposed a new estimator for autocorrelation modeling and some methodologies based on Monte Carlo algorithm. Through a collaboration in EXCELLERAT that we had, between KTH and Fraunhofer Sky, so we try to have some in-situ estimation of time averaging uncertainty. And this is very important because, as Dennis mentioned, we usually have problem with I/O and storage issues, and also it's very good to have a way for online monitoring of the convergence of statistics of turbulence simulations. So we started with proposing some novel updating or streaming algorithms for uncertainty quantification, and then we implemented them through a code which is linked to NEC 5000, but this is just arbitrary. One can choose another CFD solver, and then we can have this catalyst interface for in-situ estimation. So I'm not going to talk about this in details, and instead I'm going to use this opportunity to advertise the talk by Christian, which is going to happen tomorrow at 10:30. We have had a very interesting theoretical development regarding estimating uncertainties high-order statistic, turbulence statistics. So for instance, if we have this 3D cavity flow for a point, that we can get the signals, the time samples for U and U squared. And these two quantities are required if we, for instance, want to estimate uncertainty U prime RMS. As you see, in addition to the traditional ways, which only include estimation of uncertainty, the sample mean of this, we can combine the uncertainty, the covariance between these two. So as a result, we can get this uncertainty estimate, this narrower range here, which is more accurate compared to the standard case, which ignores the covariance between these two signals. So far we have talked about the estimation of uncertainty and also sensitivity analysis. But we should know that uncertainty can be used along with other techniques in order to drive some algorithms. So here we are talking about Bayesian optimization. So we would like to find a global optima of a system through black box optimization. But the magnitude of uncertainty in the surrogate is going to drive the sampling, the sampling from the design parameter space. So we have tried this for various types of problems, and we have observed that we can expect a fast convergence to other black box by optimization. In particular, we are not going to suffer from the so-called curse of dimensionality, which happens if we have very high dimensional parameter space. So for instance, we applied this Bayesian optimization to optimize the sidewalls of a 2D cavity flow in order to minimize or maximize the dissipation. But of course, we can apply the same algorithm to more industry relevant problems. So here we have ice, which is formed at the leading edge of an airfoil. And we would like to model this effect of ice by two spoilers, so that the flow quantities after the ice look like the same in both cases. And Bayesian optimization worked perfectly fine for this case and other examples. Finally, we have been working on the concept of multifidelity modeling. So again, we have this range of numerical simulation approaches for turbulence. So if for the outer loop problems, for instance, for the optimization or UQ forward problem, we cannot spend the whole budget on running very expensive simulations. So instead, the strategy is that we run many cheap simulations, which are low fidelity, and only a few expensive simulations, which are high fidelity. And we combine them in a very smart way so that the final accuracy is on par with the case if we had run with the high fidelity approaches. So in particular, we have proposed a multifidelity model, which is hierarchical, fully Bayesian, and also can handle simultaneous calibration of different modeling parameters in the model. And also we can have observational uncertainty in the data. So for instance, here we have applied the approach in order to estimate the variation of lift coefficient for an airfoil versus angle of attack, having only very few here, 7 data points, accurate data points. But we have much cheaper data, which are going to be combined with these 7 high fidelity data. As you see, the results, the predictions of the multifidelity model is relatively accurate. So with this, I'm going to summarize my talk, and we see that estimation of uncertainty and doing sensitivity analysis and CFD simulation is very important. It has to be done. And there are also UQ-based techniques for optimization, prediction, data fusion, which are extremely useful in the case of CFD simulations and related to engineering problems. And UQit can help developing in both directions. So in the end, I would like to thank EXCELLERAT and Flow Center at KTH for the financial support, and SNCC in Sweden for the computational time. Thank you.
Thank you very much, Saleh.